In this video, I explain the convolutional neural network as the most important model for computer vision to make sense of the visual data. After watching this video, you will be able to describe the ingredients of a convolutional neural network. Let's look closer to the deep neural networks for image classification. Neural networks are nonlinear transformation of the input image. Here you see a neural network with 5 hidden layers, which is not deep compared to today's standards of deep networks with tens of cascaded layers. The input image is flattened into a vector to match the dimension of the input layer of our neural network. That is a vector of length n by m, given an image input of n by m pixels. Each node in the first hidden layer, denoted by yellow circles, are the combination of all input pixels as the connection map suggests in the model. The last hidden layer with purple nodes is the feature vector or the representation of the image. The purple feature vector is the input to the classifier layer with the pink nodes. Here we have 2 nodes at the classifier layer, since we have 2 classes of cats and dogs. Every input image at inference time is assigned to one of these classes. There are 2 problems with this approach. In the input layer, the image is collapsed into a vector. This means that all the special information is destroyed before inputting the neural network. Our deep network neither has a clue about the shape of the image nor the adjacent pixels. Therefore, vectorization of the input image is a lossy operation and, if possible, should be avoided. The second problem is the dense connections in the fully connected network. This causes a computational bottleneck for increasing the layers and an overfitting problem due to the exponential number of learning parameters. For each connection, those are the lines in the model, at least 2 parameters are learned: the weight and the bias. Convolutional neural networks, or in short, CNNs, are to solve these problems that the deep neural networks with fully connected layers impose. The first problem with image dimension is solved by integrating 2D input layer for CNN as opposed to the 1D input of convolutional neural network. The input image can directly go in as an input to the CNN. The hidden layers in convolutional neural networks are replaced by convolutional layers. The first convolutional layer consists of special filters that operate 2D convolution on the image. This creates 2D feature maps of the input image. Successive 2D convolution operations are performed in intermediate convolutional layers between the first and the last layer to create a hierarchy of visual features for the classification task. At the end of CNN model, for classification, commonly few fully connected layers are used to transform the 2D feature maps into vector features to be used in the classification layer. During the training process, the filter parameters are learned for each CNN layer. At inference time, for a given input image, certain activations are fired at each layer. Those are the neurons that are responsive for the image. It is possible to visualize activations map for input image in a CNN. We discussed the classification task here. However, the representation learning of CNN is so powerful in learning multi-purpose visual features that we can use it as a feature extractor. For any other vision tasks, this is achieved simply by removing the classification layer after training and keeping the rest of the model, denoted in a rectangular frame here, to transform images into vector representations. What is learned during the training of CNNs? The answer is the weights of spatial filters at each layer. The size of these filters or kernels are defined as hyperparameters in the design of the model for each layer. The model is trained using a supervised loss to learn the weights of these filters during the optimization process. For a kernel size of 5 by 5, at least 25 parameters are to be learned, excluding the biases. There are multiple filters for each convolutional layer in a CNN, where each filter detects different visual features. For example, one detects edges and the others detect color and texture in the image. In the animation, you see how the image is inputted as RGB channels to the CNN. The small kernel slides over the input channel. This is a 2D convolution over the input image that creates a convolutional feature map for the first layer. Next, the bias term is added to compute the linear operation and the final feature map. In contrast to fully connected layer, where every node at output is connected to every pixel in the input, here, in the convolutional layer, only a small window of pixels is contributing to a feature activation in a feature map. This is key to reducing the learning parameters as well as computational expenses for deep neural networks. There is more than one layer in the CNN. Every layer consists of several filters or convolutional operations, nonlinear activation functions, and pooling layers to downsample the image into a compact but rich representation. Covering all the ingredients of CNN models and their variation is definitely out of the scope of this video. I end with the visualization of the filters of a tiny CNN model for our cat classification problem. This model consists of 2 convolutional layers, each having several filters, as shown in the figure via many feature maps that are visualized. This was a gentle introduction to CNN as the basic block of modern computer vision. I hope that you learned the data-driven approach of computer vision in contrast to the former signal processing approach.